So like Linda said, my presentation is is going to jump off of Robin Toonstra's presentation. She presented how the brain learns, and I'm going to do a practical application of like how do we use this information that we've gathered through research actually in our physics program. How do we utilize what we know about how the brain works in our classrooms? And part of this was because Robin's like, oh, I want to present on how the brain learns. And I was like, what am I really good at? I was like, after this year, I've taught 55 sections of physics. I was like, oh, I know how kids learn physics. All right, so we'll talk about that. If you were at Robin's presentation, the slide probably looks very familiar. She used this slide because she addressed the 4 challenges that students face when learning a new topic. What they believe, so what do they come into the classroom with? What do they know or they think they know? What can they do? And then actually physically, how do they learn? She spent a lot of time looking at what students know and how students learn. And we'll spend time there too, but we're going to also look at the 2 other aspects. So to start us off, I have a true or false question for you. True or false? The physics is difficult illness is as communicable as the common cold. Think about it a minute. Don't answer it aloud. Think about it. All right. Now, what I want you to do is this. If you think it's true, you're going to put your hands on your head. If you think it's false, you're going to put your hands on your shoulders. Go ahead. All right, and then you're going to look at your chair neighbor, and you're going to tell your chair neighbor, you can put your hands down. You're going to look at your chair neighbor, and you're going to tell them why you thought what you thought. Go ahead.
Because you don't even give it a try, you give them a before.
Okay,
you just believe it's difficult, so then you don't even so that's why physics is difficult.
All right, so the answer to this question is actually true. And it's not just for the physics is difficult illness, it's any topic. So math is difficult illness, English is difficult illness, right? But it's for any of those. And so when I have parents come into my parent-teacher conferences and say, yeah, I wasn't so good at physics, or they never made me take that, it seems really hard, my students are coming in behind the 8 ball already because what's happened, right? They've already come in with a mental mindset that physics is difficult. And I have to overcome that, right? So what are we going to do today, besides for address the 4 challenges? We're going to look at a Kohnle activity. So we'll talk about what a Kohnle activity is. We're going to use this activity to start off this presentation because often we use a Kohnle activity to start off a new chapter. So I'll give you, we'll have a chance to go through a Kohnle activity so you can feel what it's like for a freshman physics student. We'll talk about what we do in the classroom to build that long-term memory throughout the unit. And then we'll talk about the importance of practice and interleaving and review. Why are those things important? Why is homework important? All right, so the Kohnle activity. Kohnle stands for the process-oriented guided inquiry learning. Right? And it's often in physics a student's first exposure to a chapter. All the sciences use them, and they use them in different ways, but for me I use them as an introductory. And you're going to experience a Kohnle. So when you sat down, you got a colored card, and there's a task on your colored card, right? So what I would like you to do is try to get, you got rid of your colored card.
No, I didn't. We'll share.
Here, no, everybody's got to have a job. Yep, everybody's got a job. Everybody's got their own colored card. All right, so what I want you to do is you're going to make sure you can kind of sit in a group of different colored cards. So everybody in their group should have a blue, a pink, a green, and a yellow. So you may have to kind of swivel your chairs around and look at the people behind you. And I want you to read your job. So let's see, you should be clustered pretty close. Yeah, 1, 2, 2, green. Here, Tracy, can you come over here and get green? Sure. And then you've got a cluster of 4 there. And then why don't you guys want to work together there? Yeah.
You can come with us.
Go ahead. Read what your job is, because each card is a different job, and each person has a different role in this activity. So go ahead, take a minute and read your role.
Would you like to switch yours to a blue, and then we can get together? Then the 4 of us can be together. You get a timer and everything. Okay.
Oh, you're right. I moved them together. All right, come on, do you want to come and join them up here?
There, without a
Shall we I got you a blue. All right, so everyone in a Kohnle activity has a very specific and important role in this activity. My timekeepers, you'll notice you probably had a stopwatch with you, otherwise you can use your watch. Timekeepers, part of your job is to make sure that it takes no more than 3 minutes to go through a page. So there's a pacing portion to this Kohnle activity. What I would like you to do now that you've read your role, be prepared to fulfill your role in your team, and you have the Kohnle packet in front of you. So you have the next 12 minutes or so to experience this Kohnle activity with your team. Work through the packet, get as far as you can. Timekeepers, again, 3 minutes per page approximately. Yeah, what? Okay. Anybody else need a stopwatch? Okay.
So, do you have enough slides?
Here, I'll take that.
I think so. Start watching. They super confused for the archive. So it sounds like one thing, but way when it started. My thought is it might be part of here's the activity. So we're gonna okay, we're supposed to start quickly. Particles interact. Oh, great. So can you facilitate this? Okay.
I would like to hear more.
So notice as you're working through this activity, nobody works ahead. Everybody's working together and keeping at the same pace, right?
Okay. Yes, thank you. Yes, okay. It's already control.
Okay.
I'm a time manager and I facilitate timing us. So it sounds like we're doing 5 minutes as we're supposed to go down. It's different from what she said.
Good, and what's your
Thank
thing?
you for taking us.
12 minutes in total.
Yes.
Okay. Protons and okay, the question is, how does this?
So are we all agreeing?
We're all agreeing that
I think my believing in the physics is difficult is being reinforced.
What does you mean physics? Let's start with that.
So if there's one positive and one negative, it's clear on what we're trying to do.
I think you're trying us to go down.
Yeah. Intended or not.
We're the same. Okay.
They want to move away from that.
So if you look at the bottom, the key says a proton plus sign is +1 and the -1 is -1. So that
Maybe it's confused about how physics near each other.
It's just there are instructions on the first page. So you're just looking at them.
So we don't need to fill this out?
This is my role.
Not yet.
Okay, never
I'm
mind.
timing us.
Flipping pages.
So are we all clear?
Oh, yeah, you guys skipped it. We should skip the stuff, but that's
Talking
here.
to the other science teacher.
I'm sorry, I can't hear you.
Clearly at model 1, focus on the color heading.
Oh, who's supposed to?
Oh, right.
You posed the question.
So our curve is measured when we have the column handle the sum, because that's the first sheet that is does it depend on positive or negative or
This is the nanometer.
So I'm gonna build it on the next page, and actually, what you look through is the model with a chart, and you're not, the step in that section, yeah, you'll get it. So,
Now understand exactly all of
But he's doing it.
We're all very anxious. Here's what we're not doing.
Or electrophysics.
Right, that's the baseline.
We're not doing.
Oh, goodness.
Yeah,
please
I'm
come.
a mathematician, but I'm not.
Well, please, this is kind of what she's trying to debunk. She's trying to debunk things that she just
I'm
did
real
before.
she would handle it much smarter.
We actually,
We have come to the conclusion.
Everyone agrees, we know, proton, the extreme
Anxiety, students of physics have,
Have.
right, so we're there.
Are you there?
Is that the lesson you were trying to teach us?
Well, not really, but okay.
you accomplished that.
Did I? I'm sorry. I tell you
All
what,
right,
flip to the next page where the directions actually start, and then you won't have the anxiety. How does that sound? So, and all you were looking at was the model that they set forth for you, but now the directions start on the second page.
We're wondering where the counseling office is.
Well, maybe start with the head of school back.
Is that where you go to Mr. Ritchie's office?
Well, we,
You're my kind of
I'll
student.
take a look, but I'm only here for a week.
Okay, so let's combination negative one, let's not give up completely.
You need 4 volunteers to help you this morning. Like in about a minute.
Come on down.
Give information to the model, and to answer questions from Richard, what is this thing that we're writing down?
We all agree?
Look at the model. Heading.
Well, I'm doing it right.
Right.
Okay, so then these are all
We all agree.
that's a positive, that's a proton.
So you can train the
This could be dangerous.
Then
So these are going with the negative.
one Newton is the big one.
Okay, we all agree.
no,
And then those arrows.
Now that she explained what we have to do.
Okay.
Then the proton.
Opposite charge are
And the other
attractive force.
and the first page.
Oh, I see. Yeah, that's on the first page on the bottom.
You look at the two. One Newton.
Yeah. Oh, here, just one Newton is created. And she didn't even, you got that.
This is the
You're
opposite.
doing really well.
She's proton and negative.
What is the
This is
charge
the
of
between
one
electrically charged particles.
Yes.
We do always need a teacher. We're never gonna not
right.
have your.
No, I'm here as the facilitator, right? No, that's an important observation, right? That you still need me. I'm just here to like.
Make sure everybody.
The amount of positive charge.
What is the charge?
One of mine is,
There you go. It says count the number of protons present and write
Oh,
the
I was
numbers
thinking-
for number 5.
So it says, it's on the first page. What is the charge of one electron?
Okay, so electron,
Right.
minus one is.
Yes.
Okay, it's a negative one.
So then as you look from
So it should
top
be
to
negative one. Is that
bottom,
so each
Percent one.
as you look from top to bottom, 4, 6.
So these are the key at the bottom? So it's like. Yeah, so I think each one represents one. This is positive. The charge of positive proton. Charge of negative. Okay, so proton is charge of negative.
Well, I'm just
This
trying
my
to
document are
figure out what this is.
Our group said everybody else.
Look closely. I don't know.
But I think this is a key, so let's go to the key. Yeah.
Situation.
Electron charge of
Wait, is this eating you up or they eating you up? Oh, okay, okay.
I know, it's funny, because I'm like, this is working, because I'm like, dude, you just gotta pay attention to details. He's gonna love that answer, not so much.
It sounds like she's.
What is the charge of one?
That's right, exactly.
So which is.
What do you mean, Patrick? I got 100 on my phone.
This one, right?
I did this photo, I got it.
Well, I got
Mrs. Kohnle, are we ready? Do you really need to for the sheet? So, but as the amount of positive increases. Data from Model West.
To us as sort of a charitable thing.
Keeps keeping us going.
We were gonna send him down at parent teacher conferences down the hall in the hoverboard. That was how we were gonna get him from class to class. That was the actual discussion.
So we on question 5, right?
One electronic distance of 0.2 nanometers.
So
So is it 0.2 nanometers? No, it's
How many electrons?
We have someone who's in time, maybe you could tell. 15.
You only have to say
Oh,
decrease,
just
stay the same rate. So you don't have to come up with.
Y'all agree, good job, good job.
Sorry, does everyone understand the math before I'm done?
It should be specifically shared.
It says write a sentence that describes the relationship between the amount of charge and the force of attraction. So it look from the top to the bottom.
Well, maybe you could add that to his, their increase.
Each column in the data table model.
It just says using your sentence, decreases, stays the same, increases.
Interesting, really team together. Are you figuring out the right there? But at variable rates.
yeah, but I'm doing my head.
Okay.
Positive charge.
Let's go on to the buy in another
Yeah.
meeting.
Yeah.
I think you're doing that.
So do we all agree that we do not have to actually split this? Just write a simple sentence.
Yes, that was my interpretation.
Let's read your card.
Positive charge increases as we have.
Oh, your quality control.
Oh my.
As you add. But not always.
I didn't ask.
Right. So number 9, are we all happy with that answer? Or do you want more specific?
I think it's fine.
The amount of positive charge, no, the force of attraction increases as the amount of a positive charge.
Technically, only I have.
Oh, check your answer. It says it doesn't stop. Stop the quarter there.
I make sure we.
This is article.
Oh, so that
Okay, great.
she didn't write a sentence. Oh, who's the quality control person?
Oh, you have to check the sentence. Yeah, that as the charge increases, the force of attraction increases at a variable rate.
Take out your variable rate.
But it's not the same every time.
It is.
Consistent. Oh, it is consistent. It is a consistent rate?
So,
You ready for me? Oh, spokesperson.
Oh,
I am the
spokesperson.
Okay, you wrote it, okay.
Force attraction.
The answer to the question.
Charge increases, yes, good, go ahead.
Oh, okay. She had my scribble. Wow.
that shows 1 photon and 1 electron at 0.2 nanometers.
She said good.
So, okay, you're going above and beyond. You're an overachiever.
All right, I'm gonna pause you here. I was hoping we get to the stage where we get to send a spy to another team because that's really fun. But we're just gonna pause where we're at. That's totally fine. So as you experience this activity, right, like a freshman physics student would experience it.
Physics is fun.
What kind of experiences did you have? Good and bad. You can give both.
Calling on me?
Absolutely.
Well, I didn't take physics in high school or college, and the counselor said, "You will regret that someday," and I wondered what she meant. Now I
So you would have wished you had some prior knowledge.
know. Indeed.
Okay.
Yes, a lot of it.
Excellent. What other experiences?
Threes.
like when we read the first page, it was like, this is another language and we cannot do it.
Okay, so there was a little bit of frustration, but as you continued to work through it, as you turned the page,
As you came to assist us, then we
Well,
felt more relaxed.
but all I did was say, turn the page, right? That's all I did, right? But then as you started to work through it, what happened?
It was a lot easier.
It was a lot easier, right? Okay, good. What else did you experience?
Well, as a spokesperson, I realized that group work kept some people from moving forward at the pace they would like, and it kept the overachievers holding us back a little.
Putting us back, she's the overachiever.
So there's this dynamic, right? But I also think one of the things I see in this is sometimes I get my kids that are really confident in physics, sharing information and want to move faster, but then they'll hit a block, right? And they're like, well, I don't know the answer to that question. And someone else in the group will speak up, right? And all of a sudden there's this really cool dynamic that happens that it's like the kid that's labeled as the smart kid in the class all of a sudden needs someone else in the class to help them. And the kid that sometimes is overlooked gets to step up. So there's this really great sharing of information that not everybody has the information, but as a group, we can come to the answer, right? So there is a little bit of slowdown, right? There's a little give and take that happens, certainly, but there's also this dynamic of like everybody in the group is important. Everybody has a job that they have to fulfill, right? And they're all important because at some point, maybe someone you didn't expect to give information is going to give it, right? Good. What else did you experience? Anybody else?
Importance of details.
Importance of details. Yes, yes, absolutely. Especially in physics, importance of details. Good.
I had a high school physics teacher who said physics was fun. Every class he started with physics was fun. So we had fun. That was our approach.
I could try.
Yeah, you guys were giggling a lot. Yeah, that's fantastic.
Thankfully, we have some people, like not myself, but others in our group that were more gifted. But we were able to get together as a
This is
team.
our smart kid right now.
All right. So, if you want to like just rearrange your bodies in whatever way you can see, I'm going to bring come back up to the presentation. I will take the highlighters back when you get a chance. No hurries. And then the colored laminated sheets, I would like back.
At the end.
At the end, yeah. No hurries now. But the Kohnle sheet you can keep.
So you're the expert in this?
So, what are some of the values of the Kohnle? And we've addressed a little bit of this already. Student empowerment to build their own knowledge, right? You didn't need me teaching you that information. You needed me there for moral support and guidance, right, and some nudges, but you essentially developed your own knowledge through this activity. Peer support. Peer support was really important, right? You could work together to come up to the answer. That opportunity to be a contributor or an information gatherer, that role switches often. If you notice, once you started to follow the instructions, the steps were very small and incremental, right? Look at the table. What does a positive mean? What does a negative mean? The benefit of a Kohnle, very intentionally, is built as these very, very, very small steps so that students, no matter where they're at, can achieve the understanding of the material. And in some cases, right, it may decrease the stress of learning a new material. some people maybe not. But if you were working right in that, like, there's a good stress zone to work in, and if we're working in that good stress zone, it's actually, you learn new information more quickly. All right, so out of our 4 challenges, what did the Kohnle address? Mindset, right? We got it. We were laughing. We were having a good time. Physics is fun with a PH, right? There might have been some fear and mistrust initially, but as you built a group, you started to build a community, right? And imagine if we did this multiple times in a school year. Kohnles are designed to address some misconceptions maybe you had about what are positive charges, what are negative charges. Everybody kind of started with a similar prior knowledge. I don't know if you noticed at the very top it said, like, if you find something attractive, what would you do? If you find something repulsive, what would you do? It wasn't even physicsy, right? It was just this common English term, so it gave us this foundational prior knowledge that we could all build on, right?
Sarah, do you find that giving them specific jobs is better than just
Yes.
Giving them the document?
Correct. So the specific jobs is very intentional of Kohnle, partly because then everybody has a role to play, otherwise only one person typically takes over, right? Constraints of attention, you're supposed to do every page in 3 minutes. We kept the pace going, hopefully, right? And there were these metacognition and self-regulation things. Check with the teachers. One of my groups got to the graphing activity. Go send a spy to another team. Are we answering the questions correctly? You've made it to the Kohnle activity, right? All right. That would be maybe day 1 of our electrostatics unit. So then day 2, then we start the unit. So what I'm going to do is I packetize everything for my kiddos, and I've given you just a little mini, I haven't given you a whole packet by any means, but there's a little mini packet. Yeah, my parents and my physics students know exactly what I'm talking about, right? And it's funny because whenever I hand out a packet, they always kind of like, this one's really thick, Mrs. Kohnle. Does that mean the test is a long way off, or is there just a lot of pictures? You're welcome.
Do you know what the history of the Kohnle is?
It was started in chemistry, and I would say I think it started in the 90s. And it was started by a high school chemistry teacher that I know. Other than that, I can't give you more information than that one. All right, so building long-term memory through the unit. What activities do you do in the class to help build long-term memory? If you were lucky enough to attend Robin's presentation, or you were able to see it online, she talked about how do we build long-term memory, right? We have to take something from our working memory, intentionally put it into our long-term memory, and to keep it in our long-term memory, we need to retrieve it, pop it back into our working memory, and put it back into our long-term memory. And we need to do that process multiple times, and the more we do it, the more that memory is strengthened. So let me give you an example. Anybody walk down the main stairs here this morning to come down? No? Yeah? Okay. What color was the ceiling when you walked down? Right? I don't know. It's gray. It was light gray.
I go up and down every day like 10
I know,
times.
right? You saw it, I'm sure. You opened the door and you looked at the ceiling, right? It was there. Your brain put it in that color into your working memory, but it booted it out because it's like not important, right? I don't need to pay attention to this. Now, when you leave, everybody's going to look at the ceiling and you'll not forget that it's light gray. So if anybody ever asks again, you'll know, right? But it's not a test. At the end of this presentation, yeah, maybe the bonus question, right? Yeah. But it's this process, right? You actually have to like cognitively move things from your working memory into your long-term memory. So how do we do that in the classroom? Well, there are a couple challenges, right? First of all, your working memory holds about 4 to 5 items at a time. Imagine each upper school student has about 5 to 6 classes. If each class only gives them one key idea, I've already run out of space for the day. Right? So we need to get those ideas from their working memory into long-term memory. It's super important. What do I do? Well, a couple of things I do is something called a big idea. And a big idea, what I do is I chunk the information for the day into 1 or 2 key big ideas. That way and Robin used this word, we're building schema. We're building that network in their brain in which for them to attach new ideas to. The other thing I do is I make them take notes by hand. Pencil and paper, they get a packet like this that has guided notes. They have to write their notes by hand because there are research studies out there that show that writing by hand uses multiple neural pathways and increases retention. And they have a reference later on when they need to go back to their notes. Right. So this transfer of information from working memory to long-term memory only starts in class. I can only start the process. They have to finish it, but what do I do? So one of the things I do is I encourage metacognition, which is the thinking about your thinking or thinking about my understanding. If you walk into my class, I was going to give you all one of these today because we thought we were going to have a table, but they all have a block in front of them, right? Blue says, Mrs. Kohnle, you're going too slow. I get this. Hurry up. Let's go, right? I'm getting bored. Green's like, ooh, right there. Like I have to think about it, but I'm in a good place. I'm getting it. Yellow's like, whoa, 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 whoa. Hold on a minute, I need to think about this, or I'm not done taking notes. Red's like, uh-oh, right? So they have that opportunity in front of me as I'm giving my presentation or we're having a discussion to say, here's where I'm at, right? They have to be brave though. And I will tell you this story. I had one, right? The smart kid, right? That's not a thing, but that's, they get labeled that way.
Perception.
Yeah, perception. Sitting in class, we're having a discussion, all of a sudden he goes, yeah, interesting, right? Right? As a teacher, it's like, ooh, all right, yeah, we gotta make more stops like this, right? So if they're brave, and we have a discussion, you have to be brave, right? And this red block may not mean it's not that I don't understand it forever. It's just I may not understand it today. I may not understand it today because something awful just happened in the hallway and my friend just yelled at me and I'm emotionally not even there today, right? And I need you to go slower. So thinking about your thinking about this whole stress and anxiety thing, right? That plays a role with this too. So using the feedback blocks. When kids give me the question, it's not a question, when they go, Mrs. Kohnle, I didn't get it. I can't help you. Can you phrase it as a question, right? Can you phrase it, and I'll give them the words. Can you re-explain this concept starting here? Because it makes them cognitively think, where did I start to lose you? Where did it start to not make sense, right? Sometimes I'll say, where did your brain start to feel really squishy, right? So rephrasing, making them rephrase it out loud forces them to go through a process of metacognition. And then we do this thing about like active internal and external questioning of content. So sometimes I'll stop and go, all right, right now you should be asking yourself a question. What question might you be asking yourself? And I have my types of questions up on the board. And it's funny because they'll all of a sudden call it out. They're like, whoa, Mrs. Kohnle, that is a coulda, shoulda, woulda question. I was like, yeah, it is. Or a can of worms question, right? So we'll think about like, where are we? Like, is it something you can just look back at your notes and answer yourself? Or is it something that is extending? Are you connecting in new ideas, connecting in things you've learned before to help, again, build that schema, right? Another thing I do in the classroom is I actually help them reduce the illusion of familiarity. So I get this sometimes. Mrs. Kohnle, it really made sense in class, but then when I came home to do homework, I don't know how to do it. Right? Well, of course, when you have the expert in front of you doing it, it makes a lot of sense. But if you didn't think about it while you were watching it be presented, it's not going to make sense. I can watch this old house and watch them lay tile, and man, it makes sense. But if you give me tile and a tile cutter and a bathroom to do, right? Because I wasn't processing in that way. So, like, helping them teach their brain that they need to process the information in a higher level way to get it into that long-term memory so they can do it at home. I also I knew it when I was studying at home and looking at my notes, but then I got to the test and I forgot it. Right? The illusion of familiarity. When it's in front of you, you can read it and yeah, it makes sense, right? I know what Bernoulli's principle says. Yeah, and she talked about airplanes and birds and, right? But when it came to actually doing it yourself, it's again a whole nother ballgame. The illusion of familiarity. It's familiar, so I must know it, but not really. Okay. We're going to practice this because, again, I want you to have the experience of being a freshman physics student. But some of the things I do with them is I will have them work through questions with their table partner. They have to talk through the question with their table partner, and then I will randomly call on a student, and they know it's going to be random. But it puts a little pressure on them, that good stress, right? So that we got to work together to solve this problem, but I don't have to do it alone, right? We can solve this problem, and then, I might get called on to answer the question. Sometimes the thing that we did at the beginning where we did the true false and then you explained your answer, right? That's something I do in class, right? We'll talk about something and then I'll be like, okay, go turn to your table neighbor and explain Bernoulli's principle to your table neighbor. Give them a situation where we would see that. They have to say it out loud. They have to process it in their long-term memory, right? Pull it, retrieve it, and actually use it. And as they start to explain it, they start to see the gaps in their knowledge. Where do I have to fill in the gaps? Where's my long-term memory have spaces that I need to fill in? And then I always tell them, when you study, don't just look at your notes. Cover up the answer with a clean sheet of paper, rewrite it, print out yourself a new packet, redo it, redo your questions, right? Test questions come primarily out of the packet. If you can redo them, then you know you are capable of doing it yourself, right?
Do they believe you?
Well, the question, some kids can do things very quickly.
Oh, sure.
And so that's one thing I think was missing in school is how come that guy can get that done so fast? And he doesn't really understand it, because I talked to him. How do they do that?
How do they do it fast and not understand it?
Yeah,
Like, understand how they do it.
yeah.
It's so ingrained into the long-term memory. Let me give you another analogy, okay? So my husband and I ballroom dance, right? And my husband's best friend from high school, his wife used to be the secretary of the Wisconsin Polka Hall of Fame. Okay. Now, my husband and I can foxtrot, we can cha-cha, we can salsa, we can merengue, right? We've got a pretty good gamut of dances underneath our belt. But we went to go learn how to polka. And we were doing this. And this couple came up to us and said, no, 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 no. That is the old school style polka, and nobody polkas like that. Oh, teach us. Well, all you do is this. I mean, that's what it looked like to me. And I was like this? They're like, no, 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 like this. Right? Their schema is so big and they've accessed it so many times that they can just pull from it, right? And they can't necessarily explain how to do it. If I asked you to explain to me how you walked down the stairs today to get here, that would be really difficult for you. But you can do it, right?
Yeah.
Same thing. Their schema is so built up that they can access it and it's so connected they can do it without explaining. But it is because of practice.
But I met guys that well, ladies too probably, but most of them were boys. And when they go from one step to the next, they don't really have to think about it. Yeah. And that's the long-term memory.
And practice.
And that's the part I'm trying to get to. Repetitive, tracing that same step. Some don't have to do that very often, but some have to do it a lot.
Right. Right. Well, and the older you get, the more you have to do it because the harder it is for your brain to myelinate those neural connections. Yeah. That's a whole nother conversation.
And you know what I was going to say is, I'm sorry to interrupt you.
No, no, no.
But it's these subjects where they're built up one concept on the other. You know, it's really important for you to get the basic, every step. You have to understand what that step is. It's like mathematics is like that a lot. And physics is like that a lot too. If you don't get this idea, so what you're saying here is you have to continue to put that in your long-term memory. And so that means you need a review periodically.
Yes. Which we'll talk about interleaving in a minute. Yeah.
Sorry.
No. I was going to say, can you come and tell that to my students and be like, hey, you know what I know, right? Because sometimes they just look at me because I'm the teacher and I love physics. That's the only thing I ever do. I sleep under my desk because I love physics, right? All right. Good. Any other questions before I move on and I have you do an activity with me? All right. So you got a packet, right? What we're going to do is I'm just going to do a little sample about how we give notes in class, right? The first page of the packet, you'll notice there's things like learning objectives, key vocabulary words, pages in the textbook for reference. So there's all these things, right, that they have as a reference for them. We're going to skip that. We're going to actually skip the first big idea because we don't have time. But we're going to go ahead and we're going to look at Kohnle's law because, ironically, that's what you were actually working on for the vocal activity. So if you want your pencil, you can take notes. Otherwise, you can kind of just watch what I would do, which is take notes, right? All right. So Coulomb's law. Coulomb's law states that an electrical force between two charges relies on distance. Q stands for charge. D is distance. F is force. Ooh, do you see what I'm doing? I'm pulling out prior knowledge in your brain, hopefully from your long-term memory from yesterday's Kohnle activity, right? And I'm bringing it back into your working memory for storage. And K is a constant. That constant converts this idea of charge and distance to force. Right? Do you remember way back at the beginning of the year when we talked about force, what's the unit label for force? Now I don't expect you to know that, but this would be a question. Newtons, yes, thank you, newtons. Again, what am I doing? I'm interleaving. I'm pulling something back from long ago and pulling it back into the front, building that schema and connecting it in with it, right? So that, oh wait, I already know this label, it's force, it's newtons, that's something I already know, I can connect those ideas in my brain. This formula should seem very familiar to you. Again, I'm talking to you as if you were freshman physics students, right? This formula should seem very familiar to you. What formula does it seem like? And usually I'll get a kid that'll say, well, Newton's universal law of gravity. That's okay. That's why you're going to take physics with me next year.
I am, next year.
Right? Look at the similarity between those two formulas. Okay? Again, what am I doing? Interleaving, right? Pulling something out of their long-term memory, helping them connect. The value for the K constant is 9 times 10 to the 9th newtons per meter squared per coulomb squared. The value for G, which was a constant we learned earlier, was 6.67 times 10 to the negative 11 newtons per meter squared over kilograms squared. Which force do you think is going to be bigger? Which is a stronger force, typically an electrical force or gravitational force? Electrical, right? Because K is such a bigger number. We then go ahead and we talk about coulombs, the label for coulombs. We'll pull out the inverse square law, because that's a connection here that we've talked about already, right? If you look down at 12, we would then discuss what do two positive charges do, what do two negative charges do, right? What do positives and negatives do, which would have been something you would have worked through in your Kohnle activity. Again, 13 interleaves again, right? The forces between any two charged particles should be equal and opposite, which is Newton's third law that they saw earlier in the year. Again, we're pulling that information out. Let's skip down to 14 for the sake of time, because we still got some stuff to talk about.
So you're saying if you hadn't done Kohnle, that would have all been a lot harder, what you just did?
Right, what I did would have been easier, because we would have done the whole Kohnle activity. Yep, absolutely. All right, let's get down to 14. 14 gives us a story problem. We're going to practice applying Coulomb's law to compare the strength of force between two charges, which is kind of what you did in your Kohnle activity, right? We have an electrical force of 0.5 newtons that exists between two opposite charges. Do the charges attract or repel? Whisper to your table neighbor. Tell me what two opposite charges do. All right. Anybody want to volunteer an answer? Attract. Yeah, opposite charges attract. Right. Yeah, we're not there yet, but yes. All right. B says if one charge is doubled, then what is the new force value? So if I were to go, and this is what I'm telling my students, right? I'm going to go ahead and I'm going to use Coulomb's law. I'm going to say that the electrical force is equal to K times Q1 times Q2, strength of charge, divided by distance squared. If I double one of the charges, just one of them, what happens to my value of force? It doubles. Notice, Q's in the numerator, right? If the numerator doubles, what happens to my answer? Whatever I do under the right side of the equation, I have to do on the left. It would double as well. It's algebra. It's algebra. It's algebra, yeah. All right, here's what I would like you to do. I would like you and your chair partner to try to do C, right? Using the original charges, so we're gonna go back to the original charge. If the original distance is tripled, what happens? So go ahead, talk with your table neighbor about it. Oh, right, it's hard to jump in.
The force is actually
It's 9 times 4.
The D is on this. Yeah, I think so.
Okay, so let's guess, just because I'm not remembering the math.
Okay.
You're right, it's on the bottom.
So the bottom,
The new force, the new value.
so is the third on the left? So the third, the three.
But my favorite part is do you have a child in mind? No, I don't. Okay.
You know, and this is something
In the lower
that's
school.
very like that.
Okay.
All right, so if I triple the distance,
The square of the distance.
I think she got the
you got the answer? What happens to the force?
I think they will break down 1/3, one,
Okay,
it will be 1/3 of the original.
it'll be 1/3 of the original. Anybody else have a different answer?
D squared would be 9
It'd be nine times greater or nine
less.
less.
So,
All right, talk to your table neighbor again. Who's right? One of them's right. Talk to your table neighbor again.
Did you s- I don't know if you said
So 1/3, that's what was it just No.
so I think you're.
All right, you ready? Let's take a look. Let's take a look, right?
Yeah.
We're dividing by 3, which is correct. However, D gets squared. And so because D is in the denominator and squared, the force is now 1/9 this much. Right? Inverse square law. Yeah, I got it, right? Okay.
Good thing he's here.
Right.
I know.
Well, it's okay. We'd still,
We're
but-
okay, right?
yeah, we'd still be okay, right? Because I don't have physicists in my classroom. I don't have engineers in my classroom, right? Not yet. Hopefully not yet. Yeah, yes, absolutely, for sure. All right, so that's just kind of a, like,
D was squared.
did you see some of the activities we did, how the interleaving, we bring concepts back and forth and then we weave in. We talked to our table neighbors, we use that support network to help build knowledge. We'll talk about an answer and it's okay if you're wrong, right? It's okay not to know, it's just not okay being okay not knowing, right?
I remember my early high school physics teacher, he always gave an example in the real world. Like, for example, two magnets, you know, they get close together, or they have the strength of whatever that is. But as you move them further and further apart, it goes by the square, the distance between them.
Yeah.
So you wonder, how come the magnet really pulls so hard when they get close together? It's because of that.
That, yeah, magnetism follows, yep.
And so that sticks in your head a little bit.
Yeah.
So that makes so much sense because that's a story, which is right brain, which then we're having an emotional experience with it. Where this is all very left brain. There's no emotions and memory attached to that. Yeah.
Hey, that's almost 100 years ago now.
It's a powerful picture.
That hasn't changed.
So, you've gotten a little taste of maybe what a lecture or note activity would be like. Okay. So again, right, we're looking at, metacognition. Did I actually understand what that answer was and why? Did I get a chance to talk with my neighbors about it? Being able to explain it out loud. So do I actually understand what's going on, or do I have to evaluate my understanding? Finally, the importance of practice, right? You have to practice again to understand. You have to practice to remember. So how do we encourage practice, interleaving, and review? You saw some interleaving actually already in lecture, right? So one of the things I have to try to overcome is the homework mindset. Some of my students are really good at it, some of my students struggle with this, but am I doing homework to actually learn and understand the concepts, or am I doing the homework just to get it done? There is a different mindset there, right? And that mindset of like, I'm using this to practice my recall, right, is gonna put you in a better place going forward. And I'm torn by the idea of answer keys. I post partial answer keys, right? The good of partial answer keys is they get feedback right away, and feedback's super important. Feedback right away to say, yes, did I understand the concept, did I not? But if you're the student that is doing work just to get it done, I kid you not, I've seen it in the library. Homework out, computer out with the answer key. I don't get it. Right? And I make my kids do their homework, their checks in a different color, but again, you know, 2 different color pens, right? So it's an important there's an importance of establishing a mindset. Like, you have to do the work in order to understand it. And I want to give my kids who do the work the opportunity to have that immediate feedback. So I'm torn, so I post partial answer key. And we talk about why in the beginning of the year, you know, and they'll all go, oh yeah. And then you saw how we interleaved concepts in class, but then it gets interleaved again in homework. So those ideas that we talk about get brought back to homework again. And honestly, one of the best compliments I can get is my kids that are like, Mrs. Kohnle, physics is different, right? I actually have to understand the content. I can't just memorize it. Thanks, right? I'm making you learn for real.
Yeah, right, for real.
So if you look at the packet, just a couple of things that you can see the students get, right? Following the activity, there was a homework. The homework activity talked about positive and negative charges. So it brought that idea back out of their long-term memory, put it back, you know, we retrieved it. We put it in our short-term, or our working memory, and kept working through it again. There was some more practice with calculations similar to what we did in class. And then the homework extension goes one step further and has them sorting activities that they think, or objects that they think could be charged versus could not be charged. And so what I'm trying to do is dig really deep into their middle school memories, right? And pull out, well, what do they know about it? If they sort these activities, and it doesn't even matter if they sort them correctly or not correctly, I tell them, I'm like, we'll find out for what the real answer is tomorrow, but sort them out and see if you can see a pattern. I want you to start to build a pattern. The next day, they actually have a lab activity where we look at, we charge some tape. And what do the 2 negative charges do to each other? What do a positive and negative do to each other? What happens when we bring the charges closer? What happens when we bring the charge tape further? So they physically get to experience what happens. And then by the end of the chapter, which is the last page, there's some what I call the advanced practice. And so there's review questions, right? Let's pull it out of that long-term memory one more time and help you like really myelinate those memories. So all of those, we're trying to address those ineffective learning strategies. Are you actually doing the work? Are you like just reading your notes, right? Are you thinking about your understanding as we go through it? Are we building that knowledge from that initial prior knowledge of like things that attract get closer together and things that repel get further apart, right? And as we build that prior knowledge and that prior vocabulary, the initial vocabulary, can we build that understanding, right? Ultimately, when it comes to learning physics, this is my my phrase. That studying physics should be more like a porta-john than a flush toilet. It needs to sit and be revisited over and over again for it to stick.
Wow, that's quite an analogy.
Memorable